Hello, so today we're going to be going over Markov chain Monte Carlo in RevBayes, and we're going to be doing that with a coin flipping model. And I will be doing this in 4 parts. And this first part will just be an introduction to our coin flipping scenario and the graphical model used to model that coin flipping scenario. Then we will write an MCMC from scratch in the Rev language to perform an analysis. And then we will do that same sort of Markov chain Monte Carlo analysis in RevBayes, but this time using some of the built-in machinery within the language. And then lastly, we will visualize our MCMC runs and assess the convergence of those runs. Now, one thing I want to point out before we jump into things is that if we go to the RevBayes website, and then we click the Tutorials tab, if we scroll down, there is a section devoted to MCMC in RevBayes. And in particular, if we click this third one, we can see that it is also a sort of coin flipping scenario. And I will be covering a lot of the things in this tutorial. And there's some code here if you want to play around with it, for modeling this sort of coin flipping scenario and inferring parameters. And the code will differ a little bit from what I use, but the same general principles will be the same. So with that, we can jump right on into things. And for this first section, this introduction, the things that we want to try and take away from it are, first is just become familiar with the coin flipping scenario and have a understanding of sort of the statistics and how we might model it. And then we want to understand the graphical model for this coin flipping scenario, so understand visually what this model looks like. And then we want to be able to implement that model in RevBayes. And then lastly, use that model to simulate coin flips. So with our coin flipping scenario, the first thing we're going to do is we're going to imagine we have a bag of coins. And what we're going to do is we're going to take one coin at random from that bag. In our case, maybe we'll take the Iowa State 2004 quarter with a nice schoolhouse scene in the back. This is actually based off of a painting by Grant Wood. He's a famous Iowan artist, and he's probably most known for American Gothic. So that's a nice quarter to take from the bag. And so what we're going to do with that quarter is we're going to flip the coin n times and record the number of heads. And we're going to repeat that process where we flip it some number of times and then we record, out of all of those coin flips, how many heads do we have? And then kind of the underlying question is, what's the probability of that coin landing on heads? And that's what we're going to try and infer given the, what we've recorded for the number of heads. And so to model this, we know that an individual coin flip has a Bernoulli distribution, or for it landing on heads, it's modeled with a Bernoulli distribution with parameter p, where p is the probability of that coin landing on heads. So for multiple coin flips, we know that that can be just a sum of Bernoulli random variables. And in this case, we're going to keep track of the number of heads, and this is binomially distributed with parameters p and n. P, again, for that probability of heads, and n for the number of times that we flip the coin. So how do we represent this in RevBayes? And so if we start up RevBayes, the first thing we're going to want to do is we're going to want to have some number of coin flips, and we're going to say that we flip the coin 10 times. And we're going to assign, some variable, we'll call it n, the value of 10. And we do that with this arrow operator here to say that it's a constant value. It's not going to change. We're always going to flip it 10 times. And then we can do the same thing with p for our probability of heads. And we're going to say that it's also constant with this arrow operator. And we're going to say that it's a fair coin, and we're going to give it a value of 0.5. So then we take some other variable, we'll say x, and we will say that this will represent the number of heads, and it's binomially distributed. And we say that stochastic variables or random variables, we use a tilde to represent those. And we know that it comes from a binomial distribution, so dn binomial with parameters p and n. And then if we look at x, it is 5 in this case. So we made a random draw from this binomial distribution with parameters p and n. So if we did this again, and if we looked at x, it's 5 again. But if we did it again, it's also 5. But if we did it one more time, it'll be 6. So we're making a bunch of draws from that distribution. Now, if we wanted to, and that's how we can simulate data. Now, if we wanted to simulate a bunch of data, we can do that with a simple for loop. So in our case, for I in 1 to 10, we will do that same sort of operation where we say x is binomially distributed with parameters p and n. And then we will have some vector, we'll call it data, and we will say that the ith value of data is equal to x. And we just close that for loop. And if we look at data, we can see that we made a bunch of draws from that binomial distribution. Now, one thing we can do just to make sure that we have things, working relatively correctly is we know that the expected value from a binomial distribution is n times p. In our case, it's 5. So if we take the mean of data, it should be around 5. In our case, it's 4.5. And if we were to increase, instead of just simulating this 10 times, if we did it more, it should converge to 5. Now, one thing I just want to note is we used a binomial distribution to model our coin flipping, but in a lot of cases, you're going to want to use a different distribution. And you can see what's all available if we go back to the RevBayes website and click the documentation tab, and then we scroll down. If we scroll down to distributions, we can see that there's a whole bunch of different distributions available. And these are all of the ones that are implemented in RevBayes at the moment that we can use to model our situations. And there's quite a few to choose from. And if we wanted to click on one of them, since we use the binomial, we'll click on that. We can learn a little bit about it. We can learn what sort of inputs it takes and what these variables represent. We know what it returns. We have a little description of it, and we have an example for how it's used. So this is a pretty good resource to not only learn what types of distributions are available to choose from, but also to learn a little bit about those distributions. So back to our case here. Now, in our case, we said that p was 0.5 and that it's a constant value, but in reality, we're going to be taking coins from that bag, and we don't necessarily know what that value of p is. So what we're going to want to do is we're going to want to model where we think that that probability of heads comes from. And in our case, we took coins from a bag, and so we kind of have to ask ourselves, what kind of coins do we think are in this bag? Are they generally fair? Are they maybe trick coins? So we're going to need to model this. And this is what we're going to call our prior, and it represents what kind of coins are in this bag. So for our prior, we are going to need to choose some distribution that's ranged from 0 to 1, because the probability of heads can only vary from 0 to 1. And in our case, we're going to say that this probability of heads comes from a beta distribution with parameters alpha and beta. And this is a pretty flexible distribution that can model a few different scenarios depending on what kind of coins we think are in this bag. So, for example, if we thought that in that bag it was generally full of fair coins, but maybe a few of those coins, were maybe a little rusty, so they tended to land on heads a little bit more, tended to land on tails a little bit more. We could choose alpha and beta both equal to 10. We can see that the mean of this distribution here, it centers around 0.5, but it has a little, it varies a little ways away from it. But most of that density is going to be right around 0.5. Alternatively, let's say maybe we thought that bag was full of those 2004 Iowa State quarters, and we know that those quarters happen to be a little bit lighter on the heads side, so it tends to land on heads a little bit more. We can choose an alpha of 12 and a beta of 8 to kind of shift this distribution over so that more of the probability density is above 0.5. Or if we thought that the bag was full of trick coins that only tended to land on tails or only tended to land on heads, we can choose values of alpha and beta less than 1, in our case 0.4 and 0.4. Or if, let's say, we didn't know at all what we thought was in this bag, we can choose alpha beta equal to 1 to make this sort of flat line that has equal probability density all throughout this sort of range. And this might be what we would call an uninformative prior. So to do this in RevBayes, all we're going to need to do is, instead of assigning p a constant value with that arrow operator, we're going to use the tilde to say that it comes from a beta distribution with parameters alpha and beta. And this is going to error out on me because we didn't define alpha and beta. So we will assign values of alpha and beta, and we're going to give those constant values with that arrow operator. And we'll say that they're both equal to 10. So we're going to say that generally we think fair coins are in this bag. So now if we try that again with p, if we look at it, it made some draw from that beta distribution. We can do it again and see that it makes draws from this beta distribution. We'll do it one more time, but instead this time I'm not going to show you what it is. And what we can do is we can simulate data again with this unknown value of p, and we'll do it 100 times this time. So again, x is binomially distributed with parameters p and n, which in our case, this p is unknown. And then we say data of the ith value of data is equal to x, and then we just close that for loop. And if we look at data, we made 100 draws from that binomial distribution with an unknown value of p. And so we can use this data then to try and infer that value of p. So that's how we can simulate data for this coin flipping scenario. So one thing we want to ask ourselves is, what does this model look like graphically? And just as a reminder, we know that our x value, or in this case the number of heads, is binomially distributed with parameters p and n. We know that our probability of heads is beta distributed with parameters alpha and beta. And then we know that in our case, we're going to say that alpha, beta, and n are known and constant. So if you want to take a moment to try and draw out this graphical model, we'll go over it in just a few seconds. And so in our case, the graphical model looks like this. Now we can see that our data here, which is this x, it's grayed out. This means that it's clamped. This means that this is our data. This is what we're generating here. And then we see that both the x and the p here are circles. This means they're stochastic nodes, and this, this means that they're random variables and they're coming from some distribution. X comes from the binomial, so it depends on this p and n, whereas beta depends on alpha and beta. And then n, beta, and alpha are all squares, and that means that they are constant. So congratulations, we kind of sneakily set up our model for Bayesian inference. Now, if we remember Bayes' theorem, we know that our posterior distribution, in our case, this is the posterior distribution of the probability of heads given our data. We know that it's proportional to the likelihood times the prior, where in our case, the likelihood is the likelihood of binomial data, and our prior is represented with a beta distribution. So what we can do is we can use Markov chain Monte Carlo to estimate this posterior distribution, and that's what we'll be doing in future videos. So yeah.